Welcome to the latest QOD video. We're moving into chapter 6 now, which concerns itself with the electronic structure of the atom. And I've actually spent a lot of time over the last couple of days going through a lot of recent AP exams, College Board AP exams. And there's not a ton in there from chapter 6, but chapter 6 is foundational to a lot of the stuff in the following chapters, for which there is a lot of stuff. And what you find from chapter 6 is actually from the latter half of the chapter, but the first half is kind of foundational to the latter half. And so we're going to cover that, but I'm also going to cover a fairly large amount of ground in this video. And so it starts with talking about electromagnetic radiation, because electromagnetic radiation is one of the most important things that scientists use to try and probe atomic structure and molecular structure, by shining various types of light on it or other types of electromagnetic radiation and seeing how the substance responds. And so what we want to talk about with the electromagnetic radiation is really two things. That is, that electromagnetic radiation displays wave-like properties, and we'll talk about that in just a second. Electromagnetic radiation also displays particle-like properties, and this is the concept of the photon. This gets into quantum mechanics and strange things that our minds can't really build models of very easily. But we just kind of have to accept that it's true, that electromagnetic radiation displays both particle and wave-like properties. Really briefly, a little bit later, we'll also get into the fact that matter, which is made up of particles, will also display wave-like properties, which is another strange thing. So just to remind ourselves about properties of waves when we're actually talking about quantifiable properties of waves, and that is the wavelength is going to be the distance between two consecutive crests. And so that is, so the distance between the two corresponding points on adjacent waves is called the wavelength, and the unit of wavelength is going to be the meter. And so, so not only do waves have wavelengths, they also have, let's just see what we're talking about here. We're talking about two different sets of waves. This has a longer wavelength than this one, right? And lambda, by the way, the Greek symbol lambda is the Greek symbol for wavelength. But we're just comparing two types of waves here that have two different wavelengths. This has a shorter wavelength, this has a longer wavelength. Now, the number of waves that pass a given point in a particular unit time, and generally we do that as a second, is called the frequency, and that's given the Greek symbol nu. Looks like a V, but it's actually the Greek symbol nu. Things that have the unit for frequency is the reciprocal second, that is the number of waves that pass by a given point per second. But a reciprocal second, when it comes to frequency, a reciprocal second is also known as a hertz, and the abbreviation for that is Hz. And as it turns out, the longer the wavelength, the lower the frequency. The shorter the wavelength, the higher the frequency. You can think about that just if you're standing at a railroad crossing and two trains were going by on parallel tracks at the exact same speed, then the one that had the longer cars, that would be longer wavelength, there would be fewer cars going by per minute than the one that had the shorter cars, even though they're both going the same speed. So the longer the wavelength, the lower the frequency. The shorter the wavelength, the shorter the length of a railroad car, the greater the frequency with which the cars come, even if the two trains are going at the same speed. And the speed that they are going is the speed of light. And the speed of light is given the symbol c. And the value of that, and this is in the AP Chem formula sheet, is 3 × 10⁸ meters per second. And so it turns out that all electromagnetic radiation, whether or not it's visible or IR or UV or radio waves or gamma rays, all travels at the same speed, 3 × 10⁸ meters per second, and that the frequency times the wavelength equals the speed. And so the number of meters per wave times the number of waves per second is going to give you meters per second, which is the speed. And so we can do a simple problem based on this, the fact that lambda times nu is equal to the speed of light. We can do a simple problem What's the wavelength of light emitted from a traffic light that has a frequency of 5.75 times 10 to the 14th hertz? So you can turn the video off and try this on your own if you want. I'm going to go ahead and give you the solution. So we've said that c, the speed of light, is equal to lambda nu. Therefore, we can simply rearrange that because we're solving for lambda. Lambda, the wavelength, is equal to the speed of light divided by the frequency, which is equal to 3 times 10 to the 8th meters per second divided by 5.75 times 10 to the 14th reciprocal seconds. And that gives us 5.22 times 10 to the 7th meters, which is 522 nanometers. We talk a lot in terms of nanometers because the visible spectrum is in the nanometer range, in the hundreds of nanometer range. A nanometer is 10 to the minus 9th meters. And so if you've got 100 nanometers, that's 10 to the minus 7th meters. You just want to have those things in your head, that the typical wavelength of visible light is hundreds of nanometers. And so we're typically going to be talking about 10 to the minus 7th meters is 1 nanometer. I'm sorry, is 100 nanometers. Okay, so that's the wave nature of light. Let's quickly move on to the particle nature of electromagnetic radiation. And what was discovered back in the early 20th century is that energy is quantized. It is not continuous. And so, in fact, when we talk about increases in energy, it always goes up by some discrete amount. It's not some continuous thing. There is a sort of stair step. However, the height of those steps, as defined by the Planck constant, which is like 6.6 times 10 to the minus 34th joule seconds, means that the distance between those stairs is actually very short. And so at the macromolecular scale that we live on, it looks like a continuous thing like this. But if you could get down into things involving electrons and protons and stuff like this, you would see actually that it does begin to have this sort of stair step appearance. And so light does not come as just continuous quantities of light. It comes in discrete packets, and that discrete particle is called a photon. And a photon has a characteristic energy. A photon has a characteristic wavelength, a characteristic frequency, and a characteristic energy. And the energy of one photon is equal to its frequency times the Planck constant, which is the thing I just mentioned before. And the value of Planck's constant is 6.63 times 10 to the minus 34th joule second. So if you know the frequency or the wavelength of any given radiation, you can calculate its energy using the energy of a single photon using this equation. And so here we go. What is the wavelength of a photon that has an energy of 5.25 times 10 to the minus 19th joules? Well, this requires a little bit of algebraic manipulation. We know that E is equal to h nu. We were just talking about that. If we rearrange the C equals lambda nu to nu is equal to C divided by lambda, we can actually substitute this equation into this equation to give E is equal to hc over lambda. So all I'm doing is substituting that into this. And then if I multiply both sides by lambda and divide both sides by E, I will get lambda equals hc over E. And so then now I actually have something that I can plug all the values in that I've just been given here. So lambda is equal to hc over E. Here's the Planck constant, 6.63 times 10 to the minus 34th. Here is C, 3 times 10 to the 8th meters per second. The given energy for this is 5.25 times 10 to the minus 19th, not times 10 to the minus 9th. So I can fix that right before your very eyes. Oh, and that messed that up. So let's pull you back. There. Save. Restart the show. And the answer is 3.79 times 10 to the minus 7th meters, which is answer A. And if you were going to convert that into nanometers, it would be what? It would be 379 nanometers. which is in the visible, well, close to being in the visible region of the spectrum. So here are some actual useful benchmarks when it comes to light, particularly light in the visible spectrum. The spectrum of visible light is that light, for the typical human eye, is that light whose wavelength is between 400 and 750 nanometers. That is between 4 and 7.5 times 10 to the minus 7th meters. As a result, the frequency of visible light is equal to between 4 and 7.5 times 10 to the 14th hertz. Because if you multiply 4 hertz times 7.5 times 10 to the 7th, if you multiply 4 reciprocal seconds times 7.5 times 10 to the negative 7th meters, you get 3 times 10 to the 8th meters per second, which is the speed of light. And similarly, 4 times 10 to the minus 4th meters times 7.5 times 10 to the 14th reciprocal seconds also gives you 3.3 times 10 to the 8th meters per second. So that is the frequency range of visible light. And the energy range of visible light is going to be simply this multiplied by the Planck constant, which is 2.7 to 5 times 10 to the minus 19th joules per photon. So these are the so if you're working with a question that's asking you about something that's occurring in the visible wavelength, these are the sorts of answers you should be expecting to see. This would be your range for wavelength. This would be your range for frequency. This would be your range for energy. Things outside of these ranges, and you're talking about some other kind of electromagnetic radiation besides visible light. Okay, so now let's talk about how does this all relate to the electronic structure of an atom. It was noted back in the early 20th century, or even before that, that if you run an electric current through hydrogen gas or any element that's in an evacuated tube so that it's in its gaseous state, it will radiate visible light, but that it does not radiate a continuous spectrum of visible light. So by comparison, if I take a flashlight or any other sort of white light source, project that through a slit, and then put the light that comes through that slit through a prism, it will give me this the spectrum of the visible spectrum. And so this would be my well, let's not worry about which end of the spectrum is which. But if I take similarly light that comes, say, from hydrogen, I've got two examples here, hydrogen and neon, and I do the exact same thing. I take a source of light from excited hydrogen atoms, run it through a slit, run that through a prism. I don't get this continuous spectrum. What I get is a discontinuous spectrum that looks like this, which gives me 4 lines in the visible region. There are also lines in the infrared and ultraviolet regions. But in the visible region, I'll get these 4 lines. Here's neon. Neon tends to look red to us, but if we actually run it through a prism, we have lines in various parts of the electromagnetic spectrum. It's dominated by the red side. But the bottom line is to say that, once again, this is not a continuous spectrum. You've got breaks in between various lines here. And so these are called emission spectra or line spectra. And so a man named Niels Bohr in the early part of the 20th century figured out that he could work something out about the electron structure of a hydrogen atom by looking at that. And what he came to realize, or this is what he postulated, that a hydrogen atom only has certain orbits that an electron can occupy. And those are associated with specific energies. So in other words, in a hydrogen atom, there are only certain energies that an electron, excuse me, that an electron can have. And you can see here sort of a map of those energies. This is the lowest energy one, and then n equals 2, n equals 3, n equals 4. They get closer and closer together until eventually infinity is right here. So a hydrogen atom only has certain allowed energy states. And an electron that's in that hydrogen atom is only permitted to be in one of those energy states. And therefore, and it just remains in that energy state. It does not absorb. As long as it remains in that energy state, it does not radiate or absorb any energy. When an atom absorbs or radiates energy, it does it by an electron moving from one allowed energy level to another allowed energy level. In other words, a hydrogen atom can only absorb exactly the amount of energy that would allow an electron to move between one allowed energy level and another. It doesn't have to be from 1 to 2. It could be from 1 to 3. It could be from 1 to 4. It could be from 2 to 4, from 2 to 5. But it has to be the exact difference between two energy levels. And similarly, if the electron, we say, decays from a higher energy level to a lower energy level, it is going to emit a photon that corresponds exactly to that difference in energy. And that's why if we just back this up all the way to the hydrogen spectrum, that's why we only see lines in certain locations. These lines don't correspond to the energy levels themselves. These lines correspond to the difference in energy level between two energy levels. So when we run an electric current through hydrogen gas, we promote electrons into a higher energy state. And then when they relax or decay back down into a lower energy state, they're going to emit photons of light that correspond to the difference between those two energy levels. And those are fixed. And so that's why we only see certain lines. We'll talk later in the chapter about why hydrogen spectrum is so much cleaner than other spectra. This whole thing can be described by this equation in which the change in energy is equal to negative hc, Planck's constant, speed of light, what's called the Rydberg constant, whose value is given to you here, times 1 over the final energy level minus 1 over the initial energy level. So let's try a problem with that. The energy required for an electronic transition in a Bohr atom from n equals 2 to n equals 3 is equal to how many joules? Well, we're going to put in, this is called the Rydberg equation. We're going to use that as our basis for solving this problem. H is a constant, the Planck constant. C is a constant, speed of light. R sub H is a constant, the Rydberg constant for hydrogen. The final state is 3, so it's 1 over 3 squared, or 3 to the minus 2. The initial state is n equals 2, so it's 1 over 2 squared, or 2 to the negative 2. If I put all that in and press go on my calculator, I get 3.03 times 10 to the minus 19 joules, which is answer B. So there you go. Almost as quickly as the Bohr model was proposed, it ran into some problems. And so there are some things that it does really well. It is completely correct about there only being certain allowed energy states in an atom. That is true, and we know that to be true, and we're going to talk about that in more detail later. However, for one thing, the model only works mathematically for hydrogen atoms. And you saw by looking at the emission spectra that the hydrogen atom is a lot cleaner than the neon atom, for example. It only works mathematically for hydrogen. Then you have these other problems. It's impossible actually to describe an electron as traveling in an orbit, which is what Bohr proposed, for a couple of reasons. One is this thing that I mentioned at the very beginning of the video, is that matter behaves like a wave. And it's kind of a strange thing to think that if I'm walking down the street, I am actually behaving both as a particle walking down the street and as a wave flashing down the street. The thing is, if you, based on the equation for this, which is here, my wavelength is equal to Planck's constant divided by mass times velocity. These wavelengths are so tiny that they're insignificant. At the macromolecular level, I really don't behave like a wave. But an electron, which has a much tinier mass, and therefore that's going to make that wavelength much larger. An electron in an atom actually has a wavelength that takes up a significant chunk of the atom. So it's kind of hard to say on that basis where if it's behaving like a wave and its wavelength is a large portion of the diameter of the atom, where is the electron in the atom? Then there's what's also known as the Heisenberg uncertainty principle, which says that it's impossible to completely know both the position and velocity of any object at any particular time. Well, that still works out okay at the macromolecular level for people like you or me or a train, because we're so big and we weigh so much that this uncertainty is essentially zero. But when you're talking about something that weighs as little as an electron, now the uncertainty is actually larger than the size of an atom. So the best you can do is actually come up with some rules that help you define where an atom is likely to be found, where an electron is likely to be found in an atom, rather than where the electron actually is. And this all comes out of what's called the Schrödinger equation, which is what's also known as quantum mechanics. And so this is an example of a probability density for the location of the electron in a ground state hydrogen atom. And it's basically a spherical thing. And the more dots there are, the more likely it is to find the hydrogen atom there. The fewer dots there are, the less likely it is to find the hydrogen atom there. This is defined by the square of what's called a wave function. And we're not going to talk about wave functions at all. And so I'll just go ahead. But the Schrödinger equation has to do with this wave function. So on a practical level, what does this mean for ordinary chemistry geeks like you and me? Solving the wave function gives solving the wave equation gives a bunch of wave functions or orbitals and their corresponding energies. And each orbital describes a spatial distribution of electron density. And so this is actually a picture of what's called an s orbital because it's spherical. And it also gives you the probability of where you might find the electron at any given time in that orbital. And an orbital is described by a set of 3 quantum numbers. So I'm going to quickly go through the quantum numbers, and then that will be the end of this video. And the three quantum numbers are, well, the first one is called the principal quantum number. This is the quantum number that Bohr described when he talked about a hydrogen atom having discrete energy levels. And so it has the symbol n, and it can have the value of any integer greater than 0. That is, any integer greater than 1. I mean, greater than or equal to 1. So you can have an atom at the principal energy level of 1, 2, 3, 4, 5, on up to infinity, as long as it's an integer greater than 0 or greater than or equal to 1. Okay, after you've figured out what its principal energy level is, then you have what's called the angular momentum quantum number. And this defines the shape of the orbital. And you'll notice that the orbital we were talking about earlier was a spherical orbital, but they're not all spherical. And the allowed values of L, which is the symbol for the angular momentum quantum number, is any integer ranging from 0 to n minus 1. And we use letter designations to communicate the different values of L, and therefore what the shape of the orbital is. And so if L is equal to 0, we call that an s orbital, and it's spherical in shape. If L is equal to 1, that's called a p orbital, which is kind of two-lobed in shape. L equals 2 are d orbitals, L equals 3 are f orbitals. D and f orbitals start getting much more complex looking. So let's just do a quick little check-in here and say, what does that mean about what are the allowed values of n, and then what are the allowed values of L? Well, n is independent of anything. It can be any integer greater than 0. But the value of L is actually dependent on the value of n. And remember, it's any integer from 0 to n minus 1. Well, if n is equal to 1, then n minus 1 is equal to 0, and therefore there's only one possible allowed value of L. When n is equal to 2, now n minus 1 is equal to 1, so you could have 0 or 1. When n is equal to 3, n minus 1 is equal to 2, so you could have 0 or 1 or 2, and it just keeps going up like this. The number of allowed values is equal to n, but the value of the allowed values is not equal to n. That makes sense. when n is equal to 1, there's one possible value of L. When n is equal to 2, there are two possible values of L. When n is equal to 3, there are three possible values of L, etc. It's just that none of these values actually is equal to n itself. And so, as we said, an L equals 0 is called an s orbital, an L equals 1 is called a p orbital, and L equals 2 is called a d orbital. So we can say that an orbital that has an n of 2 and an L of 1 is a 2p orbital. An orbital that has an n of 4 and an L of 2 is a 4d orbital, based on these shorthands here. Finally, we have what's called the magnetic quantum number, and the magnetic quantum number's value is dependent on the value of L. And so M sub L, which is the magnetic quantum number, can have any value from any integer value ranging from negative L to positive L. And so let me just show you a table that shows you how that works. All I'm doing is expanding the previous table I showed you. We've already seen this part already. Now, when L is equal to 1, when L is equal to 0, there's only one integer between negative 0 and 0 and positive 0, and that is 0. But when L is equal to 1, there are actually three integers ranging from negative L to positive L. There's negative 1, there's 0, and there's 1. When L is equal to 2, now you've got negative 2, negative 1, 0, 1, and 2. When L is equal to 3, it could be negative 3, negative 2, negative 1, 0, 1, and 2. So an S subshell will only ever hold one orbital, but a P subshell can hold 3 orbitals. A D subshell can hold 5 orbitals, and an F subshell can hold 7 orbitals. And then what this number here is the total number of orbitals at that principal energy level. So at principal energy level 1, there's one S and nothing else, so that's 1. 2, there's one S, 3 Ps for a total of 4. At 3, there's one S, 3 Ps, and 5 Ds for a total of 9. And you'll notice that the total number of orbitals in a given shell is equal to the principal energy level squared. Well, I believe that is the end of what I'm going to talk about today. It went a while and it went fast, and the QOD will be on some fairly rudimentary stuff arising out of this. I'm not trying to kill you at all, because I'm really trying to get into the part of this that has more substance to it, which will be for tomorrow's QOD. So thank you for watching, and talk to you next time.